Nicolas Monards recorded the first noticeable fluorescence effect. He observed a bluish color in water that he had infused from the wood of a Mexican tree. Kircher observed that light passing through an aqueous solution infused with this particular wood would also appear blue. David Brewster discovered a beam of white light passing through an alcohol solution saturated with leaves would have an observable red beam. He coined the effect dispersion. John Herschel first discovered fluorescence from sulfate quinine. He called it epipolic dispersion. The name never really caught on. George Stokes expanded on Herschel's experiments with sulfate quinine, and he called the effect fluorescence. Stokes used a prism of light passing through a solution of quinine. He observed there was no effect until he placed it in the ultraviolet region of the spectrum. This is how he discovered the Stokes shift. By observing fluorescence must be of longer wavelength than the light used to excite it.
Fluorescence is quite easy to understand. The basic concept is that you have an electron that is in its ground state, and it becomes excited because it gets hit with light. S sub 0 is the ground state in this equation, and S sub 1 is the excitation state. H nu is the light that is either exciting the electron or being emitted from the electron. Fluorescence is when this electron then relaxes back down to its ground state, and it will emit its own wavelength of light and some heat. This wavelength of light will be less than the wavelength that was used to excite it because it loses some energy when it moves down through these vibrational levels that are within each excited state. So the light will come in and hit the electron, which will excite it up to an excited state and a higher vibrational state as well. It will then relax through these vibrational levels, and finally when it gets to that bottom vibrational level, it will relax all the way back down to its ground state. When it relaxes back down to its ground state, that's when the light will be emitted. This whole process takes milliseconds, which means when you look at something under a black light, it only glows while it's under that black light. As soon as you take it away, it's no longer going to glow. This is because this electron is excited into its singlet state, which means that if the electron is in a spin-up orientation, it will keep that orientation rather than changing from a spin-up to a spin-down orientation. Because you have this spin-up to a spin-up transition, it allows it to fall down through these energy levels a lot faster.
Phosphorescence, like fluorescence, occurs by an electron falling down in energy and emitting light. However, before falling to the ground state, the electron passes into a lower energy triplet state. This transition, known as intersystem crossing, is normally forbidden, but can occur due to a process known as spin-orbit coupling, which reduces the energy gap between the two states, allowing for a more favorable transition. One of the most common phosphorescent chemicals is strontium aluminate, which is found in many glow-in-the-dark materials due to its slow process of re-emitting light. Many of you are actually probably very familiar with chemicals like these, as they are common in phosphorescent dyes that coat glow-in-the-dark stars that many kids place on their ceilings. If you are confused about the visual differences between fluorescence and phosphorescence, try a simple blacklight test at home. Things that fluoresce tend to be much lighter, while those that phosphoresce tend to be much dimmer. Once you remove the light, those items that fluoresce will return to normal, while those that phosphoresce should still have a light glow to them. Unfortunately, this really only allows for qualitative observations. Since most fluorescence and phosphorescence take place at timescales that aren't really discernible by the human eye, we must make use of fluorescence spectroscopy to make the quantitative measurements that are really important for analytical chemistry. The first major component of these instruments is some sort of light source, in this case a Xenon Arc Lamp, which is a hollow glass tube that has electrodes on either end that allows an electrical current to pass through the xenon gas, ionizing it and emitting light. Now, if you were to actually stand right next to this lamp, you would actually see an intense bright light, which, as you can see, would require some form of eye protection. So this light then passes through a monochromator, which is basically just a series of mirrors and diffraction gratings, which allow you to select out only the wavelengths of excitation and emission that you are looking for. This can be done both manually and digitally through a computer, and as you can see, this allows for a really fine tuning of the exact wavelengths that you're looking for. Next, the light's going to pass through your sample, and then through another monochromator, again, just to ensure that only the wavelength you're particularly looking at is there. And so after that, it's going to pass through a photomultiplier tube, which is basically your detector, which is just a series of diodes that cause a cascading photocurrent that allows really dilute solutions to have a really high intensity. So this is a really high sensitivity type of spectroscopy. So I couldn't find a good video of what this looks like, but since all good videos deserve an explosion or an implosion, I found this video of research that is being done to describe what happens and show what happens when one of these fail. And so after this is kind of the graph that you will receive. The one on the left was done with a UV-Vis spectrometer, the one on the right done with a fluorescence spectrometer. So unfortunately this is a reference, so it kind of looks a little too near perfect. It looks almost like a mirror image. But in the real world, we don't have that kind of luxury. This is usually more of what you see. Since both the UV-Vis and the fluorescence have different exact processes of how they work, you are going to see a little more noise maybe in fluorescence or UV-Vis depending on what kind of instrument you're using.
Bioluminescent algae has become very common in recent years. The shores of San Diego were lighting up the night sky to such a swarm. In the future, these algae can be gathered until they can be used as emergency lighting and energy-efficient lighting in places where power is a large issue, such as during space exploration or in deep-sea research facilities. This is just a small part of the research that is currently underway on phosphorescent organisms.